In the last lecture, we have seen the Coulomb's law. Now in this lecture of electric field and charges, we are going to learn about electric field. So let's start. To understand physical meaning of electric field, let's consider a Cartesian plane. You can see here the Cartesian plane in which a charge capital Q is placed at origin. Origin O is there and the charge capital plus Q is here. In this condition, charge capital Q will exert a force on charge small q placed in its surrounding as per the surrounding and will exert a force as per the Coulomb's law. The distance between both the charges is OA. Let's consider OA equals to small r. Now here we can see that the force according to the Coulomb's law is here, F equals to capital Q small q upon r square. As we know that according to Coulomb's law, the force between the two charges which can be of attraction or repulsion vary as the inverse of the square of the distance between them. Now here we have the value of k 1 upon 4 pi epsilon naught, and after putting this value we will get the Coulomb's law in this form, the complete form, you can say that. Now we may ask the question, if the charge small q is removed, here the charge small q is removed, small q is here and it's gone now, then what is left in this surrounding? What is left in this surrounding? We have anything here. If we have nothing in this surrounding, is there nothing at this point A, then how does a force act when we place charge Q at A? How does a force act? To answer these types of questions, early scientists introduced the concept of field. We can see that here. According to this concept, every charge produces an electric field everywhere in the surrounding. The field exists at every point in the three-dimensional space. Whenever a charge comes in influence of another charge, the field of the first charge there acts on second charge, and the vice versa is also true. Now we can see that here electric field, it is defined as the space around the given charge in which the force of attraction or repulsion can be experienced by the other charge. It is defined as space around the given charge. This is the charge, our charge is here, and it is the space around the given charge. We can see that here the space around the given charge in which the force of attraction and repulsion can be experienced by the charge. This is called the electric field. Now the definition of electric field intensity. Always remember that electric field is different and electric field intensity is a different thing. Electric field is a quantity which we are defining as space, and electric field intensity is the strength of the electric field. Here we are defining the strength of the electric field. To look at this, it is a force that a unit positive charge would experience if placed at a point in influence of the other charge. It is a force, it's a force experienced by a unit positive charge if placed in the influence of the other charge. Or simply we can define it as force of attraction per unit charge, or you can also say that force of repulsion per unit charge. Here we go. F equals to E upon small q, the unit charge. if we divide the, oh, it's wrong, it's the inverse, E equals to F by Q. E should be here and F is, it should be here. E equals to F by Q, then force per unit charge is the electric field. And here we go, the electric field is there here, 1 upon 4 pi epsilon naught Q upon R square. The small q, you can, are you listening, are you seeing? The small q is gone, it's not here right now. The maximum times this force per unit charge is negligibly small. Maximum times this force per unit charge is negligibly small because Q is negligible. Q is a very small value which can be neglected, so therefore the force is also negligible. But if we divide the force with Q, the electric field would be finite. So electric field has a finite value and it is a vector quantity. Electric field due to group of charges. In the earlier section, we have learned about the electric field with two charges, electric field of two charges, one charges. Now we are seeing the electric field due to group of charges. Electric field intensity at any point due to group of charges is equal to the vector sum of the electric field intensity due to single charge. Electric field intensity at any point due to group of charges or the set of charges is equal to the vector sum of the electric field intensity of individual charge at that point. In this figure you can look at this figure. Here we have four charges, Q1, Q2, Q3 and Q4 exerting force at a point P, or you can say exerting electric field without charge, because charge is absent, so there is no force, there is electric field. Electric field, four charges exerting electric field at this point P. Now we have our relation, the E net, the net electric field at this point P will be the vector sum of individual electric field exerted by the individual charge. Simple. Now electric field lines. What are electric field lines? The picture of field lines was invented by Faraday to develop intuitive non-mathematical way of visualizing electric fields around charge configuration. Non-mathematical way of visualizing electric field around charge configuration. Characteristic of electric field lines. Field line starts from positive charge and end at the negative charge. If there is a single charge, they may start or end at infinity. Like this, arising from the positive charge and ending at the negative charge. The field line starts from positive charge and end at negative charge. Now, next character. In a charge-free region, electric field lines can be taken to be continuous curves without any breaks. Charge-free region, charge-free, the region without any charge. You can say this region here you can take it, this region here you can take it, this region here you can take it. This region is without charge, but we have continuous curves of the electric field lines. Third one, two field lines can never cross each other. If they did, the field at the point of intersection will not have unique direction, which is absurd. Two field lines can never cross each other. It should be remembered. Electrostatic field lines do not form any closed loop. The fourth one, electrostatic field lines do not form any closed loop. This follows from the conservative nature of electric field. So electric field lines never form closed loop. They never start from a single point and end at the same point. It never gonna happen. So see you in the next lecture. Goodbye.
La 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 da 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 da.